I know my phone was ringing. I was like, who is it? So yesterday we started working with our exponents, the properties of exponents, and we worked with the the product property of exponents. What we were multiplying, exponents have the same base. What did we do with the exponent? Yesterday we learned that there is a rule. If I'm multiplying exponents with the same base, I can add the exponents. But we went a step further. We don't want to just rely on a rule. We want to have some understanding of where it's even coming from. So we broke out our exponent. 5 to the 5th, which could be broken out this way, times 5 to the 8th. I'm really multiplying 5 13 times, getting 5 to the 13th. X to the 6th times x to the 2nd really gives me x to the 8th. So that we did right. You wrote down the rule yesterday. Any number, same base, to this, the power of a, the power of b, you could add the exponents together. Today we're going to talk about another property of exponents. We're talking about division. When we divide, notice here, and you can write this example down. This is the example we're going to work with. We have 4 to the 12th divided by 4 to the 5th. So we're dividing powers that have the same base. And you'll hear me say it over and over. When in doubt, we break it out, just so we can see what we're actually dealing with and the terms that we have. If I wanted to expand 4 to the 12th, what would it look like? What would it be?
4 times itself.
Yeah, it's going to be 4 times itself 12 times. So let's break that out. Again, we recall from yesterday that the base of 4 tells us the number that's actually being multiplied, and the exponent of 12 tells us how many times we're multiplying that number by itself. That's why we have the number 4, but we see it 12 times, 4 to the 12th. How about 4 to the 5th? 4 times itself 5 times. So you should see something like that. If we expanded this division problem, which yes, it is a fraction, but we know that fractions represent division, this is what we have right now. So looking at when we have it broken out, and we want to focus primarily right now on the broken out expression. 4 to the 12th over 4 to the 5th. Do you notice anything that can be simplified? Let's think about simplifying fractions. What do we mean when we talk about simplifying a fraction? Can you give me an example of a fraction that's 6/12? Okay, so 6 over 12, if we had the fraction 6 over 12, we could simplify that. What would it simplify to?
1/2.
1/2. Good. 6 over 12 would simplify to 1 over 2. Any other examples? 3 over 12 would simplify to 1 over 4. Absolutely. Good. All good examples. Now taking a look at this broken out division problem, which is really a big fraction. Is there anything that we could simplify? You're going to have to be a little more specific, since the only thing up on the board are a whole bunch of 4s. If you're saying the 4, what do you mean? All of them are gone? So we just don't have a number anymore?
Well, you can multiply like all of the 4s that are on the top side.
We can multiply that?
With a product?
Yeah.
Okay, so you're talking about actually calculating.
Yeah.
You could. That would be very time consuming. Not necessarily what we need to do. Yeah, if you got in a bind, you could essentially like multiply it out and figure out what it would reduce down to. Is there something else? Just take a look at the way the fraction is laid out. What do you see?
Dividing exponents.
No, right now we're talking about simplifying that fraction.
But is that a thing? You can divide an exponent.
Where do you see exponents right now?
Oh, well, put it into that. Like,
So we broke it out so that we could see something that we already know we can do. Eric, what do you mean?
1, 2, 3.
Hold on. So Eric's saying something about the 5 4s in the numerator with these 5 4s in the denominator. What value does that have? What I just circled kind of looks like a box. What I just put in there, what is the value of everything in there?
One,
How do you know?
because it's the same thing.
Same amount.
Four to the fifth power, but four to the fifth power.
Right, we know, right? What do we know about what numbers become one whole? Or what do I know here? Any number divided by
It's,
itself is 1.
yeah.
So that's a 1, and that's a 1, that's a 1, that's a 1. How does that help me?
Because now you have the last one.
So I don't need to show those 4's in the denominator because I know that any number divided by itself is 1. So my expression actually simplifies to this. 1 times 1 times 1 times 1 times 1 times 4 times 4 times 4 times 4 times 4 times 4. Do I have to show 1 times itself like a whole bunch of times? No, anything times 1, I don't have to show that 1. So what am I left with?
4 to the 7.
I'm left with 4 to the 7th. Okay. So that would be simplified. Now we're going to go through a couple words right now to figure out what's actually going on here. The dividend, divisor, and the quotient. What number on this board represents the dividend?
The thing that.
What number is the dividend here?
4
So,
to the 5th.
yeah, we're 4 to the fifth power. No, the 4 to the
4 to the 12th is our dividend. By definition, what does the dividend represent? It's the number that's actually being divided, like the number that's going to get broken up. Good. Which number here is the divisor?
4
4 to the 5th. And what by definition does our divisor do?
So a number that's being
Yes. So the 4 to the 12th, the dividend is the number that's being divided. And then that divisor is the number that's doing the dividing. Right? It's what's actually going to divide, which is 4 to the 5th. And then what about the quotient?
The answer.
The answer of our division problem, which here would be 4 to the 7th. So what is the relationship between the exponent of the dividend, the exponent of the divisor, and the exponent of our quotient? How did we get it? If I have an exponent that I'm dividing with the same base, what can I do with the exponent? I can subtract. The division property of exponents looks like this. So write this definition down so that you have this property written. Another way you may see this is the quotient of powers. To divide powers that have the same base, you subtract the exponents.
What? The free had a lesson on
I said, yeah, I could, and I was
So I like to show this example this way. This example here is 4 to the 5th over 4 to the 3rd. Because I like to show that that's a big one, that's a big one, and that's a big one. Because just like we said yesterday, you can work with a rule, but it really helps if you understand where that rule even comes from. Because now you have 2 properties to keep track of. You have the product property. When you're multiplying, we know that we could add the exponent. But now you have the division property, that if I'm looking at the same base, I can subtract the exponent. Breaking it out is still going to be extremely helpful, especially when you start dealing with other types of examples, such as right now, the exponent in the numerator is larger than the exponent in the denominator. That won't always be the case. You're going to see some examples a little bit later that may look a little different. By breaking out the expression, you can see the values of 1. You can see the 1 wholes. So once you write this, we're going to take a look at another example to see how we can continue to simplify without focusing just on rules. Does anyone need more time to write? example that we did, the 4 to the 12th over the 4 to the 5th, is the same concept as the example here. So if you have that example, you don't have to write this one with it, especially if you have it. I always like to see multiple examples, but the base of 4, like it's almost identical. Anyone need more time? That's fine. So we're going to take a look at this example here to prove why using a rule may not always be as helpful. Okay, so if we did the same thing, now we're still dividing, we have this, our base is still the same, right? We have an x in our numerator, we have an x in our denominator. If I wanted to break out the numerator, how would I break out 15x to the 6th? What would it look like? 15 and then 6 x's, multiplying everything. How about the denominator?
3 times x times x.
All right. So now if we wanted to simplify, how can I simplify? What am I able to simplify here? Okay, so I have this x and this x make 1. This x and this x make 1. This x and this x make 1. So, but it doesn't always have to be stacked. Like when I do these, I love to visually see it stacked, but that's not really necessary if they're not near each other. It could have been this x over here and that x there. They still make 1 because you're dividing. So, am I done?
No.
Why not? I still have another part of this fraction. Can I simplify that? How?
Well, what about, wait a minute, the bases aren't the same.
I can still do 15 divided by 3. That's just a fraction, 15 over 3. What is 15 over 3?
5.
Yeah, I could simplify that. So this could simplify to 5 over 1. And what am I left with? So how can I write that? Do I need to show a denominator here?
No.
Now in this example, the denominator is 1. I don't have to represent that. So my simplified expression would be 5x to the 3rd. This is a great example of why the rules can get a little confusing. If you only focus on a rule and you're constantly thinking about subtracting, yes, you could have done x to the 6th. You could have taken the 6 minus the 3, getting x to the 3rd. But so many students who only focus on rules end up doing 15 minus 3 because they're so used to seeing division that they're just going to subtract everything. That's not subtraction. It's still a fraction. It's still 15 over 3. If you break it out and actually look at what you're simplifying, I feel as if you'd have a better chance of identifying this as a fraction that can be simplified instead of just focusing on a rule. And so this is an example of why we don't want to always focus on rules. That's also probably the next layer up in terms of the division property because you have not only the base and the exponent, but you also have a coefficient. Let's take a look at this problem here. Is 3 to the 4th over 3 to the 2nd the same as 3 to the 2nd over 3 to the 4th?
No.
Why not?
Wait. Because if you're subtracting from top to bottom, it's not going to be the same.
I heard something commutative property. I heard something about them not being the
Yeah, that
same.
commutative property is kind of what I'm talking about. Because with addition, you can switch it around. But
Okay, so commutative property tells us I can change the order of addition. What else can I change the order of?
Multiplication.
I can change the order of multiplication. Good. Could I prove that these are not the same?
Yes.
How?
By writing them out.
Okay, I could write them out. If I wanted to break out 3 to the 4th, what would that be? Yep, 3 times itself 4 times. And how about 3 to the 2nd?
3 times 3.
And simplify?
3 to the 2nd power.
Alright, this a big one, this is a big one, so I'm left with 3 squared.
Yeah.
How about here?
3 times 3 over 3 times 3 times 3 times 3.
So I still have this big one, I still have this big one, but what do you notice in this simplified fraction?
Yeah, then 3 negative squared.
What's the numerator?
1.
1. And what's the denominator?
3 squared.
These are actually two very different numbers. The number on the left, if I calculate it, is 9. The number on the right here is actually 1 over 9. So just because you see those exponents, where they're placed matters. Are they in the numerator? Are they in the denominator? Do they represent the dividend? Do they represent the divisor? That will change things. Also, you're not just going to start moving stuff around. If there is a value in your denominator, that value will stay in your denominator. You're not just going to move it up to the numerator because you don't want a denominator, because then you're messing with the value. You don't want to do that. Questions? I'm going to pause this and then show you what we're going to do right after.